In all chemical reactions, energy is needed, and so the energy is actually needed in order to break the bonds. So energy is going to be released when new bonds form. So when they break the bonds, the energy releases, and when they create new forms, energy is released. Atoms now have a more stable arrangement after that energy gets released with the new arrangement of electrons. So there are two types of reactions, or two ways to talk about reactions in terms of their energy. So reactions can either be endothermic or exothermic. Endothermic reactions are chemical reactions that need a constant input of energy to continue because it takes more energy to break bonds in the reactants than is released when the new bonds form. And so endothermic literally means taking in heat. The prefix endo means inside or within. Thermic refers to heat. Heat is often absorbed from the surroundings or the environment. This results in a decreased temperature in the environment or the surroundings. So things will feel cool or cold. This could be enough of a decrease in temperature to cause a liquid product to freeze. So for example, photosynthesis is an endothermic reaction. It relies on a constant energy source, and that energy source happens to be the sun. Exothermic reactions are chemical reactions that create energy because it takes less energy to break bonds in the reactants than is released when new bonds are formed in the products. So exo means outside or out. Again, thermic refers to heat. And so exothermic literally means turning out heat. So we write the generic formula of reactants yields or gives us the products plus energy. This will result in an increase in temperature in the surroundings. So any combustion reaction would be an example of an exothermic reaction. So regardless of endothermic or exothermic, energy must be conserved. And this is the law of conservation of energy says that energy cannot be created or destroyed in a chemical reaction. However, it can change forms. So for example, electricity is a form of energy that turns into light energy. It's the same amount of energy. It always will remain the same. Endothermic reactions, that energy is stored in the chemical bonds of the product and is often referred to as chemical energy. In endothermic reactions, the products have more stored chemical energy than the reactants did. Exothermic is exactly the opposite. Their products have less stored chemical energy than the reactants. The excess energy in the reactants then gets released into the surroundings, and that's why we feel an increase in heat. So here's some graphical representations of this. So in our endothermic, for both graphs on our y-axis, we have the amount of stored energy. So down here would be a low amount of stored energy, and up at the top would be a high amount. And that's the same for both endo and exothermics. And then we have on our x-axis the direction of the reaction. So for endothermics, this line shows us that our reactants start off with a low amount of energy, and our products, we absorb some energy, which means that our products hold on to that absorbed energy, and we now have more energy in our products than our reactants. In our exothermic, we start with high energy reactants. The reaction releases energy, causing our products to have less energy. So you will be expected to be able to identify these graphs as either endothermic or exothermic. So energy is also used to start a chemical reaction, and this energy is called activation energy. So like starting a car, turning the key causes a spark that activates the burning of the gasoline in the engine. The combustion of gas won't occur without that spark. So every chemical reaction that takes place is going to need some sort of energy input. Otherwise, the reaction won't happen. And this is because the atoms and molecules of the reactants literally need to bump into each other and to collide. And so this requires those particles to move, and they only move if they have energy. And they have to have enough energy to overcome the forces that push them apart. And energy is also required to start the breaking of the bonds in the reactants. So if we increase the temperature of the reactants, the rate of reaction is going to be very dependent on various things. And so lowering the activation energy allows more particles to react. So what causes these reactions to happen more quickly? We work with the temperature of the reactants. Usually an increase causes the reaction to occur faster. The concentration, or how much of the reactant there is. The surface area of the reactants, and then if there is a catalyst present. So now we're going to take a look at each of these in a little more detail. So the higher the temperature of the reactants, the more increased the rate of reaction is going to be. Particles of the reactants have more energy, so they're moving faster, which increases the likelihood of bumping into one another and colliding with a greater force. So, for example, you put an egg in a frying pan and you turn up the heat, causes the egg to cook faster. The higher you turn the burner on, the faster the egg will cook. Also, the opposite, storing food in the refrigerator, reduces the amount of particle collisions, so it slows down the rotting or decomposition process. So when we look at concentration, we're really looking at the number of particles of a substance in a given volume. A high concentration of reactants gives us a high reaction rate because there's just simply more reactant particles available to collide. The particles are more crowded, which increases the collisions. The number of collisions and oftentimes the force of those collisions as well. All of this increases the reaction rate. For solid substances, the amount of surface area available influences the reaction rate. So only the matter at the surface of a solid is exposed to the other reactants. So when you look at the head of this hammer that's rusting, only the outside is rusting because that's the only part that's exposed to the oxygen. So more surface area that's exposed, the more ability of it is there to react. So how do we increase surface area? We increase surface area by crushing or pulverizing or making a powder of a substance, and it exposes more surface area for the reactants. So like a sugar cube versus regular sugar. The regular sugar will have a greater surface area than the sugar cube because the sugar cube can get crushed and then increase surface area. So if we have a catalyst present, catalysts have special jobs. Their job is literally to increase the rate of reaction. Catalysts don't change and they do not get used up. So they get to be reused over and over again by multiple reactions. Some reactions will not even occur without a catalyst. It is not actually a reactant, it's just a helper. It decreases the amount of activation energy that is needed. And so living things depend on catalysts to speed up the cellular chemical reactions. When we talk about living things, we call catalysts enzymes. So without enzymes, some reactions inside our bodies could take up to billions of years, whereas with the presence of enzymes, they can take up mere hours. So catalysts really speeds things up. So here we have a little diagram that shows us we have our reactants at some energy level, and if you trace the red line up, you can see that it needs way up here. It needs to reach that much activation energy before the reaction will take place, and then it produces the products. If we have a catalyst present, the reactants still start at this same level, and you can see the peak now of this hill is much lower than if there was no catalyst present. So when we need less energy, it takes less time to accumulate that energy so the reaction can proceed more quickly. And so that's what catalysts do. They decrease that amount of activation energy. I think I skipped this slide earlier on, and this is just a couple of graphs, endothermic and exothermic graphs that show your activation energy. And so the amount of activation energy that is needed is the measure from the reactants up to the peak of this hill. So this is the amount of activation energy, I'll label it AE, that endothermic reaction takes. In the exothermic reaction, we can see the level of the reactants, and then you measure up to the peak of the hill, and that's the amount of activation energy required for that reaction to proceed. And so both types of reactions require activation energy. In general, exothermic reactions need less activation energy because they have high energy reactants. So that is chemical reactions and energy.